by and large set ourselves up in coordinate geometry. We are seeking to move to the next echelon, the other entities related to coordinate geometry. But some generalized entities, some generalized formulations in coordinate geometry, which will apply across everything that we learn in coordinate geometry. Some of those things, at least one of those things I would want to expose you to in this class today. Now, first of all, if you recall, an expression of this kind is a generalized second degree expression in x and y, right? This equal to 0 is a generalized second degree equation in x and y, right? Now, a condition would cause this to represent a pair of straight lines. If you recall that condition, the condition that will cause this to represent a pair of straight lines was this: ABC, HG, HG, FF equal to 0. The pair of straight lines will be real if h squared is greater than or equal to AB. Otherwise, the pair of straight lines will be imaginary. But pair of straight lines only after this becomes 0, this determinant becomes equal to 0, would you examine whether those lines are real or imaginary? One way or the other, this is the condition for this to represent a pair of straight lines. Similarly, this same equation, under this condition, when it represents a pair of straight lines, under different conditions, it will represent different things. For example, if A is B and H is 0, we will learn down the line that this represents a circle. For different combinations of A, B, H, F, G, and C, this will represent different entities: pair of straight lines, circles, parabola, ellipse, hyperbola. All of it is packaged in this single equation. Based on your choice of A, B, C, H, F, G, you get one entity or the other, either a pair of straight lines or a circle, or one way or the other. So whatever it represents, and whenever it does so, this essentially is called a second degree curve. This essentially is called a second degree curve. You know, the circle, the parabola, the ellipse, the hyperbola, they are all second degree curves. They are all second degree curves. So suppose this represents some second degree curve. It could be a circle or a parabola or an ellipse or a hyperbola. Suppose this represents a second degree curve, right? Some second degree curve, and this is part of a second degree curve that this represents. It could be part of a circle or an ellipse, hyperbola, etc., parabola, whatever be it, right? I'm keeping some things in the black box. You're not ready to consume those things, so I will not get into an explicit explanation of when a parabola, when an ellipse, when a hyperbola. Forget all of it. All that you need to know is that this same thing could represent all of them based on choices of the coefficients A, B, C, H, F, G, etc. Right? So this is, let's say, part of a second degree curve, whatever be it. Parabola, ellipse, circle, hyperbola, whatever. And let me look at a straight line Lx plus My plus n equal to 0. Let me look at a straight line Lx plus My plus n equal to 0. Alright. And let's say this straight line Lx plus My plus n equal to 0 intersects this second degree curve at A and B. Intersects the second degree curve at A and B. This is Lx plus My plus n equal to 0 is a chord of the circle. Not circle, chord of the second degree curve. Chord of the second degree curve. This line. Now, I will carry out an operation as follows. This is a second degree expression. I will carry out an operation. And do you realize this is a second degree term? Because the sum of the powers of x and y add up to 2. This is also second degree term. Why? Because the sum of the powers of x and y add up to 2. Sum of the powers x and y add up to 2. 1. This is a degree 1 term. This is a degree 1 term. This is a degree 0 term. Right? Now, I want to make this expression homogeneous. I want to make this expression homogeneous using this expression, right? So, I carry out the following. I want to make all terms degree 2 terms. I want to translate every term into a degree 2 term. Now, this is what I do. I don't tinker with this. This is anyways ax squared. I don't tinker with this. This is anyways a degree 2 term. I don't tinker with this. Anyways a degree 2 term. Now, these two terms are degree 1 term. Right? 2gx plus 2fy. Now, if I multiply it with an expression of the kind lx plus my, then do you realize that x into x degree 2, x into y degree 2, y into x degree 2, y into y degree 2. This then becomes a degree 2 expression. This then becomes a degree 2 expression, right? Look at C. I do a following lx plus my, I'm sorry, lx plus my plus n, right? Lx plus my plus n whole square. Just what I do is I'll just modify this a little bit with your permission. What I would choose to write the line instead of lx plus my plus n equal to 0, let me write the line as lx plus my equal to 1. Every line can be written like this, lx plus my equal to 1, isn't it? Every line could be written like lx plus my equal to 1. So I do this lx plus my, I do this lx plus my whole square. This is the line. Let me just rewrite, tinker with the looks of the line. I can write every line in this form, lx plus my equal to 1. Then I multiply this term with lx plus my. This will become a degree 2 term. C is degree 0. I multiply with lx plus my whole square. It will become a degree 2 term. Degree 2 term. Right. X square, xy, y square. All are degree 2. So now this entire expression has been converted into a degree 2 expression in x and y. Degree 2 expression in x and y. Now, using what? Using lx plus my equal to 1. That means now, the operation that I have performed is called homogenizing. Is called homogenizing. Homogenizing the second degree curve. This was my second degree curve. Homogenizing the second degree curve. Using lx plus my equal to 1. Using lx plus my equal to 1, I have homogenized the second degree curve. Now, on homogenizing the second degree curve, I get a homogeneous second degree equation in x and y, yes or no? This was my second degree curve. Using this line, I homogenize the second degree curve, and this is called the homogenized second degree curve. This is called the homogenized second degree curve in x and y, yes or no? This is not the same as this. This generalized curve was homogenized. Using what? Using this line, lx plus my equal to 1. Resulting in what? Resulting in a homogenized second degree curve in x and y. Resulting in a homogenized second degree curve in x and y. Are you all okay with this? Now, what does it stand for? Let's see the geometrical entity that this stands for. The homogenized second degree curve, let's see the geometrical entity that it stands for. See, think of it. What are the nature of terms? Something into x squared, right? Because we'll have an x square coming here and an x square coming here, I consolidate. So it will give me like something into x squared plus. It will give me something into xy, 2h. Then there is an xy coming from here, 2g into m and 2f into l. There is a xy coming from here and there is a middle term, 2lm into c coming from there. So something into xy plus. Look at the y squared term, something into y squared. Y squared terms are, a y squared term comes from here, a y squared term comes from here, and there is a m square c, another y squared term. So then they're all put together in this location. That equal to 0 is what I get. That means, what does this reduce to? This reduces to a homogeneous second degree equation in x and y. Something into x squared plus something into xy plus something into y squared equal to 0 represents what? A pair of straight lines passing through the origin. A pair of straight lines passing through the origin is. So, one thing, given a second degree curve, if you homogenize it with the help of a line, you end up getting a pair of straight lines passing through the origin. No matter what this second degree curve represents, a circle, a parabola, or an ellipse, or a hyperbola, the moment you homogenize this second degree curve with a line in a manner that I've suggested, the geometrical entity that results is a homogeneous second degree curve in x and y, which is a pair of straight lines passing through the origin. So homogenizing this with this will give me what? A pair of straight lines passing through the origin, no matter what this represents. That's part one of the story. Right? That's part one of the story. Now, suppose A has coordinates x1, y1. This line, Lx plus my equal to 1, intersects this second degree curve at A and B, where A is say x1, y1. A is say x1, y1. X1, y1 will satisfy this equation because it's a point on the line. Will cause Lx plus my to become equal to 1. The coordinates of A will cause Lx plus my to become equal to 1. Similarly, coordinates of A will also cause this expression to become 0. Why? Because A is also a point on this curve, so it will satisfy this equation as well. So x1, y1 causes this expression to become 0. x1, y1 causes Lx plus my to become equal to 1. Right? Now I want to see if A, which is the point of intersection of this line with this curve, also lies on this homogenized curve or not. I want to examine if A satisfies this equation or not. That means if A is a point on the homogenized curve or not. That's a check that I want to be able to perform. Clear? See, if this expression becomes 0 when you replace x by x1 and y by y1, then A must be a point on this curve. If the coordinates of A cause this expression to become 0, then A must be a point on this curve, right? Let's check. Okay. A causes Lx plus my to become 1. So this becomes 2gx plus 2fy. It causes Lx plus my whole squared also to become 1. Now, what are you left with? You're left with ax squared plus 2hxy plus by squared plus 2gx plus 2fy plus c, which becomes 0. A will cause that expression also to become 0. That means A causes this entire expression to become 0. That means A must be a point on this curve. Right? A must therefore lie on this homogeneous second degree curve in x and y. A must therefore be a point. A therefore must be a point on the pair of straight lines that this represents. What did this represent? This represented a pair of straight lines passing through the origin. Right? Right? And A must lie on that pair. Similarly, B will also lie on that pair. That means, if O is the origin of coordinates, then one thing, on homogenizing a curve with a line, I get this curve, and this curve must pass through A and B, and it will also pass through O, and it will be a pair of straight lines passing through O, A and B. Right, isn't it? It's a pair of straight lines passing through O, but this is also a pair of straight lines passing through A and B. Therefore, what does this represent? It represents, suppose this is A, it represents this line AO and BO. It represents a pair of straight lines passing through the origin as well as A and B. So it represents a pair of straight lines AO and BO. It's the combined equation of AO and BO. So, given a non-homogeneous second degree equation in x and y, a second degree curve in x and y, given a line, if the line intersects the curve at A and B, then you could homogenize this second degree curve with the help of this line. When you homogenize, then you get this curve, which is what? A pair of straight lines passing through the origin. So the homogenized curve is a pair of straight lines passing through the origin. Not only that, it also passes through A and B. So this represents what? The combined equation of AO and BO. Is that okay or not okay? So homogenizing a curve with a line will give me what? A pair of straight lines passing through the origin and the point of intersection of the curve with the given line. This is what it does. Right? You understand this idea of homogenizing? It's a very potent concept. It's an extremely potent concept. We will deploy this in our next unit, which is circles, and we'll really find effectiveness in doing this. But so far so good, right? Make sense to all of you? Concept of homogenizing.